Hi, my name is Steve Casner, and along with my teammates Dave Babcock and Joe Frederick, I'd like to welcome you to the IBM 1620 Junior booth at Vintage Computing Festival West 2020. This is our fourth VCF, and we're excited to share with you the progress that we've made this year towards building a simulated card reader punch device for the 1620. The IBM 1620 was IBM's low-end scientific computer in the early 1960s. It was relatively inexpensive and was often used by engineering firms for design calculations and by schools to teach computing. The IBM 1620 Junior project has a goal of producing a technically accurate replica of the 1620 using modern technology. This all-volunteer project is sponsored by the Computer History Museum. When completed, the IBM 1620 Junior will be used by the museum's education department to let visitors experience hands-on what computing was like in the 1960s. There are four major parts to the IBM 1620 Junior: the control console, a software simulator, a console typewriter, and a simulated card reader punch. Starting with a real IBM 1620 control panel, our team replaced the incandescent lights with LEDs and plastic toggle switches with metal ones for durability. A Raspberry Pi 3B Plus processor provides the compute power. Custom-designed interface circuitry drives all the lights and switches, matching the real machine's varying light patterns and intensities. A new simulator is being developed. It's written in C and precisely mimics the IBM 1620 down to the machine cycle level, turning on all the individual lights on the control console. To recreate a reasonable facsimile of the 1620's console typewriter, our team modified an IBM Lexmark Wheelwriter 1000 electronic typewriter by designing a firmware-driven serial interface board to interpose between the keyboard and logic board. We developed custom keycaps replicating the unusual layout of the 1620's typewriter. At last year's VCF, our presentation focused on a side project to extend the console typewriter into a general-purpose ASCII computer teleprinter called Cadet Writer. Using our design and assembly instructions, several computer hobbyists have already built their own Cadet Writer for use with their favorite vintage machine. The final component of the IBM 1620 Junior project to be developed is a simulated card reader punch. Punch cards were the primary computer input and output medium in the 1960s and 70s. Real punch cards are not practical for our use today, so we're building a miniature simulated card reader using a text file on a USB memory stick to represent a deck of punch cards. These images show a prototype of that device. The final version will have a proper case, enhanced graphics and animation, and will play the actual sounds of reading and punching cards as recorded from a real IBM 1622 card reader. Now we're going to demonstrate what it was like to develop software for the IBM 1620. You would write your program in assembly language and punch it into cards, use an assembler to translate your program into machine code, load your program into the 1620 and run it, then debug any problems, revise your code, and repeat the process. Programs were typically written out on coding forms, particularly if they would be punched into cards by a professional key punch operator. Flowcharting was also often done first to work out the logic of a program before coding. Our replacement for key punching is to type the program in a text editor and save it as a file on a USB memory stick. The 1620 required a 20-minute wait after power on for the core memory to warm up. We won't simulate that. Next, we load the IBM SPS assembler into the IBM 1620 Junior. This is done by inserting the SPS's card deck into the read side of the card reader punch and pressing the load button. The computer now reads the assembler into its memory and starts running it. This takes a while because the 1620 was pretty slow. A modern laptop may be 1 billion times faster. Cards are read at a rate of 500 per minute, equivalent to a few hundred kilobits per second. We'll speed up through the boring part. Then we remove the SPS card deck from the output tray and insert our source program deck into the card reader.
The program switches and start pass 1 of the assembler.
Then pressing Start begins the execution of pass 1 of the assembler. The source cards are read and an internal symbol table is created. To run the second pass of the assembler, our source deck is removed and reinserted into the reader. A memory stick representing a stack of blank cards is put in the punch side of the device.
We change the switches and we start the assembler pass 2.
The source cards are read for a second time, assembled, and the binary translation of the program is punched into output cards. The symbol table is printed on the console typewriter.
Now pass 2 is done. We remove our source code. We take the punch binary deck and insert it.
We then take the binary card deck that we just punched and placed it in the reader.
We can run the program.
The IBM 1620 Junior is reset, so it's ready to start again.
Reset the machine. Load the demo program.
The load button is pressed on the card reader to read and transfer our program into the computer's memory.
And start the demo program running.
This simple program runs pretty quickly. The IBM 1620 can multiply two 1,000-digit numbers in one instruction.
And that's the complete demo.
That completes our demonstration of assembling and running a sample program that calculated 2 to the 234th power, which is a 71-digit number. The elapsed time was 5 minutes and 27 seconds. But as every programmer knows, the largest share of development time is spent debugging the program when it doesn't work correctly. On the IBM 1620, that was often done on the console. IBM 1620 programmers could use the console to step through the execution of their program one instruction at a time, or even one machine cycle at a time, and examine the processor registers to find where their code went wrong. And that's how programs were developed on the IBM 1620 in the 1960s. The IBM 1620 Junior team would like to thank the Vintage Computing Festival staff and volunteers for their contributions to the project. If you have any questions or comments, please contact us. Thank you for watching our demonstration.